Good morning. My name is Murtala Aminu, and I also apologize for Dr. Falah, who is also a track chair and is down with the flu. As the chairman says, we looked into design and performance analysis of uplink schedulers for smart metering over LTE. Just a quick background of LTE. LTE is known as the long-term evolution, which is the mobile technology that is popularly known as 4G. LTE started looking into machine-type communication, whereby smart metering can be looked at machine-type communication in Release 10, which is not captured here, but it was just an overview in Release 10. They started enhancing and putting some guidelines and specifications in Release 12. And as you can see in Release 13, they've enhanced what the requirements should be in terms of bandwidth and timings, which is critical in machine-type communication. And further releases are also in development, Release 14 to 15. So what we are looking into is how can we guarantee quality of service for machine-type communication over LTE. As you're all aware, LTE is primarily for human-to-human communication, which is voice, and also data, whereby people browse Google. So the challenge is when you introduce machine-type communications, whether it's sensors or smart meters, vehicles, Internet of Things, how will you guarantee that the underlying technology will guarantee quality of service of those traffics over LTE? Because primarily mobile operators are more focused on your voice application and your data, so they are not interested in any other traffic. So there are quite different ways in providing quality of service over LTE, which consist of things like grouping systems, whereby you group your applications, or coordinated things like relay. What we looked into is the scheduling algorithms. So how can we, because in the 3GPP, which is the body that underlines LTE, they've left the scheduling algorithm as open, so every provider can decide which type of algorithm to use. So what we looked into is the scheduling algorithm in terms of how can we allow this machine-type communication devices coexist with your mobile applications. So we don't want the competition between resources between these devices, but we want them to be reused. So what we looked into is to classify our traffic into different classes. One of the classes is we defined real-time applications and delay-intolerant applications. So things like emergency traffic, fault traffics, which are real-time applications, we class them into one group. We then have another class of non-real-time applications. So for example, the application we looked in this work is the smart metering, which we can classify as a non-real-time application, but is delay intolerant. We also have another class, which is a real-time and delay tolerant. These are things like your mobile applications, whereby voice over IP, you find that it's real-time, but it can also accommodate up to 150 millisecond delay. And the last class we have is non-real-time application and delay tolerant, things like HTTP traffic, FTP, and other applications that you use on your mobile phones. What we tried to do is LTE as a technology classified something called quality of service class identifiers. So they have different classes of the present application that we use today. But the timings of those applications is not compatible with some of the applications that are coming in terms of machine-type application, things like e-health, monitoring, and stuff like that, because the timing of LTE is so high. So what we try to do is to introduce new QCIs. Sorry. How do you use the pointer? Sorry? Okay, sorry. So the LTE standard defined 1 to 9 quality of service class identifiers. So what we try to do in our own case is to introduce more and class our traffics, as I've shown previously, into different classes and giving them, depending on their own traffic classifications, because if you look at machine-type communications, there are different timings that are required for each application. So for example, our smart meters, can tolerate up to 50 milliseconds, but in some cases, things like health applications will require lesser times. So based on that, we derived this table and introduced new QCIs for our algorithm. For our simulation, we used UpNet as a simulation tool, and we tried to break down the traffic that we used in this. So in the work we've done, we've used these applications, which are mostly LTE applications, voice, HTTP, FTP, and we now try to introduce our smart meters and fold and classify them based on these different classes that are previously highlighted. This is the simulation topology. So we use the random displacement of smart meters and user equipment in a range of 500 square meter, whereby we now introduce some of these traffics based on the previous table here into this, and we just use different servers just to capture the traffic from one point to other. In this work, we looked at a single hop scenario whereby all the applications send in directly to one E node B base station to the other, but there are different approaches which we are looking into whereby we use multi-hop using either picocells or microcells depending on the location. What we've tried to do is we've compared the algorithm we derive with the normal common standard algorithms, which is round robin, for example. Round robin is like a TDMA-like algorithm whereby it's like first in, first out traffic pattern. So when the buffer is full, your traffic doesn't get dropped. It's just wait on the next cyclic time to deliver the traffic. That brings in a lot of delay in terms of when the network is congested. And it also doesn't look into things like your channel quality and things like that because it's just a cyclic pattern. We also use proportional fair. Proportional fair tries to look at your channel quality. So for example, if you look at this topology here, this node here, which is quite a distance to the E node B, proportional fair looks at what's the resource allocation to this device in relation to the device that is closer to it. So in those cases, when the channel quality is good, it gives you, it allocates resources. Then we now compared it with our own class-based algorithm, which also has both channel quality index and we use fairness, Jane's fairness algorithm to do that. Some of the performance metrics we use to measure is throughput, whereby we looked at the total number of bits delivered in a simulation time. We looked at our packet delivery ratio in comparison with both LTE traffic and our smart metering traffic. We also looked at the end-to-end delay. This delay is the delay that takes from the time the packet is sent from a device up to the time it gets to its destination. Selected results that we use, probably this is small, I tried to make it bigger, but no, you can see that when the network is getting congested, this is with 400 devices, it gets, the packet gets dropped when you're looking at things like proportional fair and round robin, but with our algorithm, we almost had near 100% delivery ratio. We also measured the delay, which is really important in terms of some of these applications, because this algorithm, in this application, we look smart metering, but it can also accommodate some time-critical applications because of the maximum delay we received is less than 3 milliseconds, so which is good. We also looked at our packet delivery ratio when we increased the node size. So as you can see here, it's 400 devices. We tried to increase it to 1,000 so that we can look at the scalability of the algorithm, how can it accommodate larger areas with more nodes. In conclusion, we concluded that even though we are coexisting and using the same resources, our algorithm is able to maintain quality of experience of the LTE user, because that's very important. We don't want having voice drops calls while machines are using, because there's a white paper that says in 2020 you have over 50 billion connected devices. So this shows you that there will be a problem in the future whereby if all these applications will be using LTE as a communication tool, then we need to have a better quality of service. We also ensured that the separation of both LTE and smart metering applications, so we reused the same resources in terms of our resource blocks rather than using one resource. So when the user is not using, mobile phones are not using those resource blocks, it gets allocated to your smart meters. And also classifying this traffic into groups helps you have a guaranteed resources rather than being treated as best effort. And also we've concluded that within that 500 square meter, even though increasing your network size from 400 devices to 1,000, the algorithm is scalable. And thank you.
Thank you very much.